Hello. Let's talk about lines in space. So I got to be honest, this is one of my favorite things to do. This is one of my favorite topics in Calc 3. I don't know why, but I love looking at linear equations, and then we're going to get into plane equations and how they get to interact. And I just find it really cool. So I'm hoping that you guys will too. Up until this point, we've been talking about vectors, and vectors have a lot to do with this, but this is our first real application of the power of vectors within a multivariable calculus space. So without me getting too much on my soapbox, let's go. So we're going to talk about lines in space, and I'm going to make sure I compare and contrast a bit between lines and planes. The thing is, if I want to do a line in space, that's what I want something like this. A plane in space is something like that, and their equations are different, and we need to make sure that we're careful of that. Lines in Lines in space don't have an equation. They have multiple equations because they are written parametrically. And that's one thing you have to remember. So if I ever accidentally say, find the equation of a line in space, I really mean find the equations of a line in space. A line in space is defined by two things. It is defined by its direction vector and a point that it goes through. Any point, doesn't matter. Okay, think of it as point slope form, except instead of slope now, we have a direction vector. And the three equations that form a line in space are x equals x sub 1 plus at, y equals y sub 1 plus bt, z equals c sub 1 plus ct. In other words, the direction vector creates the coefficients and your initial point gets added to it. It is that easy. Now, where does it get more complicated? It gets more complicated where you're trying to find the direction vector of a line, or you're trying to find a point on the line, and we'll get to that, okay? So I need to stop saying so. In all these videos, I've realized I say so all the time. So it says find two sets of parametric equations of the line pointing in the direction of v equals 2, negative 3, 4, passing through the point 1, 5, negative 9. I said find two sets. That means there's different ways to write a line, just like there's different ways to write a line in, regular 2D. So let me tell you what I'm talking about. And in fact, you know what? I'm going to make three sets because I can, and you're stuck with me. So if I wanted to find one set, I'm going to do the easy way out. I'm going to use the direction vector. I'm going to use the point that they give me and write a parametric equation. X equals y equals z equals. The vector creates the coefficient of t, so 2t, negative 3t, 4t, and then the point just gets added on to the end, plus 1, plus 5, minus 9. There is one set of parametric equations for this line. Hooray, done. Then it says, give me another set. Well, just like lines in 2 dimensions can be unsimplified, so can line in 3 dimensions. If I have a direction vector of 2, negative 3, 4, I could just say, you know what? If 2, negative 3, 4 is a direction vector, so is the vector 4, negative 6, 8. It's still a direction vector. It has a larger magnitude, but since a line has infinite length, I don't care about the magnitude of the direction vector. So another set of parametric equations could be 4t plus 1, y equals negative 6t minus 6, and z equals 8t minus 9. I didn't mean 6, I meant 5. Pardon me. I'm using the same initial point. So 4, negative 6, 8. And the point is 1, 5, negative 9. That's that. Okay, well, I'm not just going to multiply that by another thing. I'm going to do something else. 1, 5, negative 9 is one point on this curve. What if I wanted to use a different point? Well, how about I use the direction vector? If 1, 5, 9 is definitely on the line, and the line's direction vector is 2, negative 3, 4, wouldn't that mean that the point 1 plus 2, which is 3, 5 minus 3, which is 2, 9 plus 4, which is 13, is also on the line? Because my direction vector tells me how to get from one point to the next on that line. Oh, you're at a point, go 2 in the x direction, -3 in the y direction, and 4 in the z direction, and you'll be at another point on that line. So I just did that. So another equation for this line is x equals 2t, y equals -3t, z equals 4t, plus 3, plus 2, plus 13. Cool beans. All right, now find a set of parametric equations for the line passing through the points -3, 0, 8 and -3, -9, 5. Fine. When we're in 2D, I always used to tell you, you really need 3 things to make a line: a slope, an x, and a y. Now that we're in 3 dimensions and we need a parametric set of equations for a line, I still need a slope, but in this case it's a vector, an x, a y, and now a z. So a point and a slope is really what I need. Well, let's see. I don't have a slope, but if I have 2 points, I can sure as heck make a direction vector. So this direction vector would be 0, -9, -3. And if that's my direction vector, I can use either point for the line. I don't know, I'm just going to pick the first one. So this is going to be x equals 0t, y equals -9t, z equals -3t, and then I'm going to use that initial point -3, 0, 8. One other thing that we can do is, since the direction vector is just that, a direction vector, the magnitude doesn't matter so much. So if I didn't want to use 0, -9, -3, I could also use 0, 3, 1, because that's parallel to 0, -9, -3. But Mrs. Faber, they go in different directions. I don't care. It's a line. It extends in both directions anyway. I don't care if my direction vector points to the right or to the left. All right? So I'm going to have, there's that so again, x equals 0t, y equals 3t, z equals 1t, and then use the same initial point or the other point. Nobody cares. Cool. Now, this next part, I'm going to be totally honest, the symmetric equations of a line, I hate them. They're just, I don't like them. You need to know them, but if it were me, I would write everything in parametric form every single time. I'm going to show this to you. I'll ask for it from time to time so that you're familiar with it. But if you're going to write a line yourself, I highly encourage you to write the line in parametric form. That said, what are the symmetric equations for the line? It's really that somebody said, hey, all of those equations have a t in them. What if we solve them each for t and then set them equal to each other? That's really all that happened, okay? So it says create symmetric equations for the 2 examples above. So I'm going to start with this purple set. 2t plus 1. Let me shrink so I can see them. So x equals 2t plus 1, y equals -3t plus 5, z equals 4t minus 9. And if I want to write this in symmetric form, I'm going to rewrite this as a t equals. That'll be x minus 1 over 2. I'm going to rewrite this as a t equals. It's going to be y minus 5 over -3, which you will often see written as 5 minus y over +3. Oftentimes, we don't like having a negative on the bottom. I sure as heck don't mind. But you will notice in the book, they rarely have a negative on the bottom. And then last but not least, t equals z plus 9 over 4. Since each of those are set equal to t, we can set them equal to each other. So it becomes x minus 1 over 2 equals 5 minus y over 3 equals z plus 9 over 4. And that is what's called the symmetric equation of a line. Now, it's said to do this for the 2 examples above, and there's a reason I said for the 2 examples above, because something seriously funky happens when I look at this one. If I take this equation right here, I just left it as 0t minus 3. Really, that becomes x equals -3. And if I try to rewrite that in symmetric form, I have x equals -3. What were the other ones there? Y equals 3t. And z equals t plus 8. Right? Right. If we want to put that in symmetric form, I can't solve x for t. So what I do is just solve the ones for t that I can. So this is t equals y over 3, t equals z minus 8. Set those two equal, put a comma there, and say x equals negative 3. What that means is if you are missing a t in one of your parametric equations, it just becomes a comma and you write whatever that variable equals off to the side. Find symmetric equations for the line passing through 2, 3, 4 and perpendicular to vectors v and w. Well, if I want the line to be perpendicular to two other vectors, something that's perpendicular to two other things is the cross product. So this time, if I want to find the direction vector for the line, I have to do a cross product, and so I shall. I hope you're not just watching me and you're doing this on your own. I got a perpendicular vector of negative 38, positive 2, negative 14, which you can use as is, or you can shrink it down. I don't really care. And it has to pass through the point 2, 3, 4. If I want to write that in symmetric form without creating a parametric set first, in parametric form, you add the point. In symmetric form, you subtract the point. So symmetric form would be x minus 2, y minus 3, comma, z minus 4, and then my vector goes underneath, negative 38, 2, negative 14. Ta-da! There's equations for a line. What do I have next here? Wow, there's a lot of other stuff. Okay. Good news is this other stuff isn't too bad. Determining if lines are parallel, coinciding, intersecting, or skew. Since a line has like an infinite number of forms, we have to be able to tell if two lines are the same line, are parallel and next to each other, or are intersecting, or are skew, which is when one line's up here and another line's down here, and they never actually intersect, but they're also not parallel. All right. So two lines are coinciding if their direction vectors are parallel and the vector connecting their initial points is parallel to the direction vector. What? What that means is if I have two lines that are coinciding, and I'm sorry that the lights are out, I'm alone here in the dark. If any of you has like a Roomba laying around at home that doesn't work anymore, but it moves, it just doesn't vacuum, and your parents are looking to get rid of it, do me a favor. Glue like a tall stuffed animal to it, bring it in here, and I'm going to make it go around the room so that my lights stop turning off, and I'm not talking to you in the dark. Back to math. Here's a line. Here's another line. These are parallel. Here's a line. Here's another line. These are skew. Here's a line. Here's another line. These are intersecting. Here's a line. Here's another line. Those are coinciding. Coinciding lines and parallel lines have the same direction vector. However, coinciding lines and parallel lines, I lost my train of thought. Coinciding lines and parallel lines have a unique difference in that coinciding lines are really the exact same lines, so they contain all the same points. Now, if I look at this line right here, 3t minus 5, 2t, t plus 6, and I look at that line right there, the first thing I'm going to do to decide if they are parallel or coinciding is see if their direction vectors are parallel. Because if their direction vectors are parallel, I know that the lines go in the same direction. So L1 has a vector of 3, 2, 1. And L2 has a vector of negative 6, negative 4, negative 2. And those are definitely parallel. So I know these lines go in the same direction, but I'm just not sure if they're the same line yet. In order to figure out if they are the same line, what we can do next is this. Here's two parallel lines. If I consider this the initial point of the green line, and this the initial point of the blue line, and I make a vector out of them, The vector connecting the initial points is totally different than the vector creating the lines themselves. However, if blue and green are coinciding, if I find this initial point for blue and this initial point for green and connect those, that vector points in the same direction as the line itself. So I have vectors for L1, L2. I'm going to have my point on L1, which is -5, 0, 6. And I'm going to connect it to my point on L2, which is 4, 6, 9. I'm going to call it the P vector, the vector connecting the points, which is up 9, up 6, up 3, R 9, 6, 3, 3, 2, 1, and -6, -4, -2 all parallel? Yes, yes, they are. So these lines are coinciding. Two lines are parallel if that last vector I created isn't parallel to the other two. I said write two parallel line sets of equations and prove that they're parallel. So if you want to create parallel lines that do not coincide, you just want to use the same direction vector. There we go. Use the same direction vector. So let's call this vector, 514 is going to be my direction vector. And +3, -5, +8. Sure. There's a line. If I want a line parallel to that, my coefficients of t either need to be exactly the same or constant multiples of the previous one. X equals Y equals Z equals 514. Let's make the next one -5, -1, -4. And let's make the next one have an initial point of 0, 0, 0. Here are two lines. They are at least parallel right now because they have parallel direction vectors. Now, whether they are coinciding or parallel remains to be seen, so let's check that out. Let's find a vector connecting their initial points. One of them has an initial point of the origin. The other one has an initial point of 3, -5, 8. So the vector connecting them is the vector 3, -5, 8. Is that parallel to 514? No, which means that these are parallel lines and not coinciding lines. There we go. This video is getting long, so I'm going to split this into two parts because I really want you to be fresh and focused on the next part. So I am going to stop this video here and call this a day. I haven't thought of a joke before now. What jokes haven't I used for you guys yet? Hold on. Really bad joke. What kind of bra does a mermaid wear? An algae bra. Get it? Algebra? Algae bra? I know. Guys, I got nothing. I got to pull my kids' joke books out. I swear I'll do better later. Have a great day.